meeting is being recorded.
Hi everyone, thanks for joining AWM Pitt Grad Seminar. Today we have two speakers. Our first speaker is Leah LeJeune, and Melinda Klekzinski. So our first speaker topic is effect of cross immunity in a multi-scale cholera model. And Melinda will talk about the construction and interpretation of pollination resource complexes. So I would request Leah to proceed.
Okay, I'll get this set up and let me know if my slides aren't transitioning. Sometimes I have trouble getting it set up properly. Okay, are my slides moving?
Yeah, looks good.
Okay, thank you. All right. Just want to get the spotlight. Okay, great. Awesome. Thank you, Farjana, for your introduction. And also thank you for the invitation to speak today. I'm very excited to share with you some of my dissertation work on my cholera model, particularly focusing on the effect of cross immunity in a multi-strain model. I'm a 6th-year grad student at the University of Louisiana in Lafayette, planning to graduate in May. Woohoo! So we're getting close to being done. So I just want to share with you some of the research that I've done in the process. So to start, I'm not sure how many of you have played the video game, The Oregon Trail, but growing up, I watched my siblings play hours of this video game. It focused on the westward expansion of the United States and, simulated different difficulties that settlers had to deal with during that time period. One of those was the disease cholera, where when you got a notification in the video game that you were infected with this, you knew that it was kind of game over because it was, when untreated, a pretty severe disease. It can kill within a matter of hours through severe dehydration, through vomiting, diarrhea, etc. So, as I said, I learned about cholera primarily reading about the United States in like the 1800s. And a common question that I got this summer when I was presenting my research at different places was, how relevant is it to model cholera? Isn't it pretty much eradicated? And the answer to that is yes, in a lot of countries that have highly developed infrastructure. But when it comes to countries where the infrastructure isn't as developed, or that have suffered severe damage to that infrastructure due to like natural disasters and such, cholera still is highly prevalent. So looking at this map here, we see cases reported within the last 20 to 30 years mapped out. And we see that it, again, is still pretty prevalent in a lot of areas of the world today. So we want to continue to further our understanding of this disease in order to try to create effective control measures to moderate its spread. So one of the most important things to consider when we want to model this disease is how it's transmitted through the environment. So cholera is a bacteria that can survive in an aquatic reservoir. So this could be a river, a well, a pond, etc. It can grow and proliferate in the environment, and it can also compete between different strains of the bacteria that are present in the environment. So again, this little cartoon a friend of mine drew highlights how, again, it is very prevalent in a water source, and settlers back in the Wild West, they used to mark a particular water source as contaminated by placing the bones of a dead skull, I'm sorry, like the bones of a dead animal there to mark future travelers to stay away from that water hole, because it was a very deadly disease when not properly treated. And the water source can get infected either just naturally from the bacteria occurring, or through infectious waste, or waste from an infectious individual entering that water source and contaminating it. Again, highlighting why, when you don't have like working infrastructure, like water treatment plants, et cetera, even just physical distance from a waste area to like clean drinking water, it's much easier for these water sources to get infected and for contamination to occur, and for individuals who drink from these water sources or use these water sources to get infected. Now, transmission can also occur between humans by interaction with waste from an infectious human, although it is arguable that the transmission source that comes from the environment has a much higher effect on infecting individuals. However, the bottom line to get from all of this is that because of the high prevalence of the bacteria in the aquatic environment, we are required, when we want to model cholera, to add an additional compartment to the standard SIR model. So S standing for susceptible, I for infected, and R for recovered, representing the compartments that a host goes through during the course of the infection. We add to that compartment P that represents the pathogen presence in the environment. One additional aspect of the biology that we need to acknowledge before continuing on to our model is that of the presence or the prevalence of serotype strains within the cholera bacteria. So serotypes are distinct variants of the bacteria that differ with respect to how they interact with the immune system. So when you're infected with a particular strain of bacteria or one of these particular serotypes, you gain immunity to that particular strain, but you also gain a degree of cross immunity to the other strain that you would encounter in the environment. Two common cholera serotype strains that we see are observed in recent outbreaks are Inaba and Ogawa. So we're going to restrict our model analysis to these two serotypes. And one of the really wonderful things that that serotypes allow us to do within a model is assume that the parameters between the strains are going to be identical. Basically just how serotypes work. They tend to have the same transmission dynamics, the same rate of recovery. In this case, the same rate of bacterial shedding into the environment, et cetera. So before I show you the equations that we construct for this, I'm going to walk you through the compartmental graph that's underlying our system of differential equations so that it makes a little bit more sense before we see the actual equations. So we're going to start with our susceptible compartment up here at the top, and we're going to follow this diagram down to the left to get an idea of one individual's path through these compartments. So if you're susceptible, you can get infected with our first strain and enter the infectious compartment for strain 1. And we have these double arrows representing the transmission or the transition between S and I1, because we know that we have two possible ways of getting infected. You can get infected through interaction with an infectious individual, or you can get infected through interaction with a pathogen in the aquatic environment. So the pathogen compartments are represented by the blue squares, and the pathogen interaction with the host is represented by the dotted lines. So we can have our infection from strain 1, and then recover from that, or die, but hopefully recover. And then we can be infected by the second strain. So we have these red arrows here to distinguish infection from the different strains as the lines are crossing throughout the compartment. And we can enter our compartment where we've been infected with strain 1, but are currently infected with strain 2. Now notice, again, we have two transmission routes, one from host-to-host interaction, another from environment-host interaction. But both of these transmission rates are now moderated by this parameter 1 minus gamma, where gamma is the cross immunity parameter. So it's again that degree of immunity that we get from after recovering from that first time infection. So gamma ranges between 0 and 1. If gamma was 0, we would have absolutely no cross immunity. There would be no protection to a secondary infection. And when gamma is 0, we would have, I might have said that backwards. When gamma is 0, we have no protection. You're fully susceptible to being infected by that second strain. When gamma is 1, you have full cross immunity. I always get those two mixed up. But if you look at the diagram, you look at how the parameters are set up, you can see which one can lead you to full cross immunity. So that is when gamma is equal to 1 and gamma is 0, you get no cross immunity. So this leads us to a system of 9 ordinary differential equations. Our susceptible compartment are strain 1 and strain 2 first-time infection compartments, our recovered compartments, our secondary infectious compartments, and then lastly, we have our pathogen compartments in the environment. We see that cross-immunity term moving individuals from the recovered to secondary infectious compartments. And also, we in this particular initial model, we do represent the growth of the pathogen in the environment with a logistic growth term. Now, in general, compared to the time scale for transmission dynamics and like host infectious dynamics, the growth of the pathogen tends to be pretty slow. So to make things a lot easier for ourselves, the first thing that we're going to do before we begin to analyze the model is take this growth component or this growth rate G to be 0. So that'll significantly simplify the pathogen equations. In addition, we're going to consider beta and beta 2 to be equal. So this is the rate of infection, whether you've been infected once before or whether this is a secondary or third or fourth infection over time. And we're going to take our shedding rates from a first-time infection versus a secondary or tertiary infection to also be the same. So alpha being the shedding rate of the bacteria into the environment from an infectious individual. What these assumptions allow us to do then is to define another compartment Y sub J that's going to be the proportion of individuals infected with strain J. And this allows us to consolidate our system down from 9 dimensions to 7, which is still a fairly large system, especially when, if you're like me, you sometimes struggle to work with systems in dimensions larger than 1 on those really bad days. But the dimension reduction by 2 dimensions still is helpful and makes this system a little less unwieldy. So we move into the standard analysis for these types of models, starting with deriving our basic reproduction number. Now, the basic reproduction number is defined to be the number of secondary infections conferred by a single infectious individual during that individual's lifespan. And this is a pretty important threshold in in a lot of biological dynamics, but you see it. I mean, I think most of us are pretty familiar with it now. After the pandemic, there was a lot of publication of basic reproduction numbers and a lot of different news sources. And here I've taken our basic reproduction number for this system, and I've broken it down to kind of highlight the role that each of the transmission routes plays in the behavior of the disease. So our first term here, beta over mu plus nu, we have beta, the host-to-host transmission rate, moderated by the population turnover rate mu and the recovery rate nu. And then our second term in this basic reproduction number is given by alpha, the shedding rate, times delta. That's our environment to host transmission, moderated by R, the decay rate of the pathogen in the environment, times our population turnover rate and our recovery rate. So once we've derived this basic reproduction number, we can show that our disease-free equilibrium, given here below, our susceptible population is going to be 1 because this system is normalized. So when we sum all of our host populations at any time, we're going to have that our whole system is just 1 because we're looking at the proportion of individuals. And we see that this is globally asymptotically stable when our reproduction number is smaller than 1. Now, this is a pretty standard result and not something we're super interested in because, the global asymptotic stability is actually, knowing that it's globally stable is pretty neat. But the thing that most people are more interested in when modeling disease dynamics is what happens when your disease is actually present and not about to die out. And that happens when our reproduction number is greater than 1. When this happens, we have a few different results. We first have the existence of 2 boundary equilibria. So this is when one strain of the disease is present while the other is absent. And the values of those strains are represented by these equations below. However, these two are always going to be unstable. So what that means is that if you're at either of those boundaries where one strain is present and the other is absent, if you perturb away a little bit from that equilibrium and introduce the absent strain into the environment, that's always going to take over. We're always going to be moving away from just having one strain present, and we're going to have that there are two strains present. And what this indicates for us, and we're able to actually prove, is that there is a unique coexistence equilibrium. So there is a point where we're going to have both strains staying in the environment. Now, unfortunately, the basic stability results, the basic analysis that's used to show stability is pretty difficult to do here because our expression for our equilibrium is very complicated. But when we look at numerical results, we see most often that our coexistence equilibrium is going to be stable. But we want to know a little bit more. We want to be able to show some stronger analytical results than just resorting to looking at the numerical simulations. And we can get some of those results using disease persistence theory. And when our reproduction number is larger than 1, we can see that our disease is going to persist uniformly in our population. So to give a snapshot of what that looks like, we look at this diagram here. So here we can look at the origin, and this was going to represent our disease-free equilibrium. So we don't have any strains present here. We have no cholera in our population. Along each of these axes, the axis represents the boundary where one strain is present, but the other is absent. So the dots on the axis are when you have, these are your boundary equilibrium that I mentioned in the previous slide. And this persistence result basically says that when our reproduction number is bigger than 1, this coexistence equilibrium represented by the red dot in the interior of the positive quadrant, this is going to basically attract our solutions. So our solutions are only going to stay within epsilon of the boundary for a finite period of time. Essentially, they're going to be, in this case, when I talk about solutions, I'm talking about the solutions to the infectious populations. So our populations of infectious individuals are going to be drawn towards this coexistence equilibrium. Now, this doesn't mean that they're going to converge to some stable, steady state where they just have a stable value over time. This could mean a periodic solution, but this does tell us that the disease is going to stay in the population. It's not going to die out, and it's not going to do anything super crazy. So we want to know, though, specifically what does the disease do in the population over time within this persistence result. So we turn to a biological scenario observed or published in a paper in 2006 to get an idea of what we would ideally like to be able to model with our model, what we would like to observe with our model. And that is the behavior that we have termed serotype cycling. So basically, looking at this diagram here, one of our serotypes is represented by the red solution, one's represented by our blue here. And what we see is that the serotype cycle in dominance over time. They don't stay at a stable, steady state. One doesn't dominate while the other dies out, but you have a dominance for a period of time from one strain. The other strain kind of lays low for a little while before that one begins to take over. The other one lays low, and then eventually that one takes over again, and so on and so forth. The biological mechanism behind this isn't clear, whether this is a result of mutation, which when we consider data from another source, they speculate that the mutation is probably not the thing that triggers the cycling, because it's common to see mutation from Ogawa to Inaba, but it's a lot less common to see mutation back from Inaba to Ogawa. So mutation seems like maybe that's not really what's causing the cycling. We're speculating that maybe this could be when we consider different regions that are infected. It could be that one population is infected with one serotype and then gains immunity to that, but another population is infected with the other. And when there's interaction between these two populations, if they have immunity to one strain and the second strain is introduced, it might be possible for that strain to then dominate for a little while. Not kill out the other strain, not outcompete it, but dominate while the other strain lays low before they again switch in their dominance within the infectious population. So this was switching behavior observed in Bangladesh, or cycling behavior observed in Bangladesh. In Haiti since 2010, they've seen serotype switching, although it's not a long enough time frame to say whether there is switching just from one to the other or whether there's been cycling observed over time. Now, a paper from 2002 proposed a model for modeling serotype bacterial diseases with multiple serotypes. And this is the model that the paper from 2006 uses. And in the analysis done in 2002, they posit that there's a correlation between the behavior of the oscillations of the solution and the cross-immunity gamma. Now, the system that they're analyzing in this case is very similar to ours, but they also have an additional forcing function built into their system, and they don't consider the pathogen compartments. So we consider, okay, what's going to happen if we introduce a forcing function, and how do we do that? How do we biologically, reasonably incorporate that into our system? And, oh, there we go. I'm sorry. Yeah, I forgot the order of the slides quickly. Okay, so before I talk about the forcing function, I'll get to that in just a second. I want to talk about the influence of gamma in the system that we have so far. So when we choose a set of parameters and we change gamma from 0 to 1 and observe the behavior, we see that as gamma increases from 0 to right about 0.5, we see that these antiphase cycles, that behavior that we saw, it's pretty similar to what we observed in that diagram representing Bangladesh. We see that we do have this like cycling and serotype dominance. The thing that we don't see, though, is sustained periodic behavior, these like sustained antiphase oscillations. Over time, they dampen out and converge to the coexistence equilibrium. And then as gamma increases to 1, so this would be when we have full cross immunity, we see that it actually appears to converge to the disease-free equilibrium. But when gamma is at about a 50% protection rate between stray protection from getting infected by the other strain, when you've been infected by one strain already, we see that we have a lot of that cycling behavior. So it seems to follow that correlation that the other model had put forth. So now we talk about introducing this seasonal forcing function, or the forcing function that I mentioned from before. For us, it's going to represent seasonality. Because cholera spreads through the aquatic environment, it makes sense that you would have higher caseloads during the rainy season, when there's a lot more water to be interacted with, essentially. So we take our environment to host transmission parameter, delta, and we rewrite it as a seasonal forcing function with a period of 1 year. And we say, if this gives us what we want from our system, does this give us that sustained antiphase oscillatory behavior that we saw from the Bangladesh data set? When our degree of seasonality is very, very large, at 0.9, we see that our antiphase cycles that we see in the unforced system actually very, very quickly synchronize into in-phase cycles in the forced system. Now, one bonus is that we do get the sustained oscillatory behavior. We do get that more standard periodic solution that's with our undamped oscillations, but they're in phase and not antiphase as we had hoped to see. So we think, okay, what else can we change in our system, or what's maybe the difference between our system and that other system that would make us not see these antiphase oscillations that we would hope to see? And it turns out, so if we explore our degree of seasonality a little bit further, we try to see, okay, if we make it very small, is that going to give us that sustained antiphase undamped oscillatory behavior we wanted to see? And the answer is kind of. From a biological standpoint, we're going to have that sustained antiphase undamped oscillatory behavior for a much longer period of time that behavior lasts for a while before convergence, when the seasonal forcing function is the degree of seasonality is very small. In the end, the unforced system still converges to that coexistence equilibrium, and the forced system still converges to those in-phase oscillations. But for the intents and purposes that we care about biologically, we could say that we see that sort of sustained anti-phase behavior. However, one of the main differences between that system I mentioned before and our system is that underlying their assumptions, they do a very similar consolatory, not trick, but they consolidate their system down by a few equations in a similar way that we do. But in their initial model before consolidation, they actually consider the presence of an additional compartment where you can be infected with both strains at once. This is called co-infection. We don't consider that. Certainly co-infection can happen, but it's reasonable to assume that co-infection is much less likely, because when your immune system is already triggered by one infection, you're not necessarily going to be able to be infected with that second bacterial strain. So we don't include that in our system, but when we do some simulations with the co-infection compartment just for kicks, we see that we do get that sustained undamped antiphase oscillatory behavior. So it seems that the additional inclusion of that co-infection compartment, it adds an additional nonlinear term in the consolidated system, which seems to be enough to perturb our solutions away from synchronizing according to the periodic solution. It perturbs it enough to have that antiphase behavior instead of the synchronized interphase behavior. So future work in this model includes analyzing our model further when considering a co-infection compartment. And then one of the big things that I want to do next is use a multi-type branching process with the stochastic system to determine the probability of the switch in serotype dominance. As we saw in the Bangladesh data, it wasn't, the switching time wasn't uniform throughout that data set. So we want to know, maybe if we use a stochastic approach to this, we can better understand when that switch is going to happen, which leads to better understanding of how to handle the disease when we know an outbreak is going to come, similar to how we treat the flu nowadays with getting vaccinations to the strain that we expect to have. So these are the sources that I've used in this work so far. I always want to give a shout out to my advisor for his support of the research, and the NSF grant that supported this research. And also, I recommend that if you're interested in cholera, you buy yourself a plush cholera toy. I have one on my desk. Apparently there's a website that sells them, and it's a fun place to visit. So I'll take any questions now. And again, thank you for your time and attention.
Thank you so much. I'm going to stop recording and we'll take questions.